Hi, and welcome to our second session of on thermochem. And today's class is pretty chill because all you have to do is you have to know four different ways that we can communicate enthalpy changes. And it's just a matter of articulating them. So I can say the same thing four different ways, and that's what we're going to learn, the four methods. So before we do that, let's review or let's talk a little bit more about change in enthalpy. So the delta H, or the change in enthalpy value, depended on the quantity of the substance that had undergone a change. Because of this, we can use molar enthalpy constraints to represent an endothermic or exothermic reaction. So molar enthalpy is like the enthalpy change per mole of a substance. So in an endothermic enthalpy changes situation, it's reported as positive, and for an exothermic, enthalpy changes are reported as a negative value, okay? Which you know. Exothermic changes involve a decrease in enthalpy of the system, because remember, with an exothermic reaction in the Q or in the surroundings or in the water, we have an increase in temperature. If there's an increase in temperature, we call that an exothermic reaction. However, we know that the delta H is the same but opposite. So in an exothermic reaction, the delta H is under 0, and that gives us a negative value. For endothermic changes or an endothermic reaction, we have an increase in enthalpy, right? And we have an increase in enthalpy because the Q is a negative number, because the temperature is going down, right? And therefore, the delta H is higher than 0. Note, the sign convention represents the change from the perspective of the system, right? And the system is what is causing the temperature of the water to go up or down, and we consider that the surroundings. So we use the surroundings to find our Q. We know that our Q is equal to the delta H, except it's opposite. So if the Q is positive, delta H is negative. This means that it's an exothermic reaction. If the Q is negative, the delta H is positive, and that's an endo. I know I'm repeating myself, kiddos, but that's okay, because sometimes repetition is good. Sometimes it's kind of annoying, but sometimes it's good. If there is an increase in the temperature of the surroundings, this then implies that an exothermic change has occurred in the system. So it's deep dive, saying the same thing. The system released energy into the surroundings, therefore the enthalpy is lost from the system, so we write this as a negative change. I know I'm repeating myself, right? But it's okay, right? If there is a decrease in temperature, kiddos, right, in the surroundings, then this applies that it's an endothermic reaction, which makes sense. The system took in energy from the surroundings, therefore the enthalpy is gained by the system. So we write it as a positive change. So positive and change in terms of the delta H for an endothermic reaction. Where the endothermic reaction, and we have a negative change, a negative delta H for an exothermic reaction. That's your foundational knowledge to this whole unit. Once you get that, you're like a rock star. So method number 1 is just talking about molar enthalpies of reaction. So this cool, very fancy thing is just a way to show molar enthalpies of reaction. So we're going to go through which each of those symbols mean, and you're going to see that it's really not a big deal. So what needs to be included in this awesome molar enthalpy of reaction? So when reactants and products are in their standard state, they are at a pressure of 100 kilopascals, an aqueous concentration of 1.0 moles per liter, and they are liquids and solids are in their pure state. So let's talk a little bit about what is included here. So in this little part here, that is your reaction type. And your reaction type could be any reaction if it's not specific. A little c means complete combustion. F is formation. A little d is decomposition. And then we have something simple as, oh, it's a solution or a dilution. So first thing is make sure after your delta sign that you are specific depending on what the question is asking for the reaction type, right? Your delta H just means enthalpy change. This little guy just means standard state. That's all it means, no big deal. The M just means molar, so this is per mole, right? per mole of a substance. And finally, at the very bottom, you write the substance that we're speaking about, or the substance in that particular example. So if we're dealing with methane, for example, we'd put CH4. That's all that means. It's not a big deal. So if you get a symbol, or yeah, like this, and it's populated, you should be able to tell me what the substance is, what the reaction is, and what your delta H is. So to communicate a molar enthalpy, both the substance and the reaction must be specified, like I talked about you before, or talked with you before. So here's an example of a formation reaction, formation of methanol. So when 1 mole of methanol is formed from its elements, when they are in their standard states at SATP, 239.2 kilojoules of energy is released. So how do we communicate that? Well, here we have formation, right? And we have our substance. And we know that this is energy is released, which means that it's an exothermic reaction, right? This means it's exothermic, which means your delta H is negative, and that's why this is here. And notice how there's only 1 mole of this, so that's why it's per mole. And we know that there's 239.2 kilojoules of energy per 1 mole, because it's already specified in the balanced equation that's 1 mole in that particular case. So here's another example, the combustion reaction. So the complete combustion of 1 mole of methanol releases of 725.9 kilojoules of energy. Note that the above reactions are balanced for 1 mole of the compound. Very, very important. That's where this came from. Notice that. That's what we had to do in order to convert this to 1. Okay, if there's a 2 here, then we have to do something different. We actually have to take this number, right, and then multiply it by 2. But that will come in another example. So don't even worry about it for right now. So for a complete combustion, here's our little C. Here's methanol. Here's our amount, our delta H, which is negative because releases, which means that it's an exothermic reaction, right? And also, that's pretty much it. And it's negative 725.9 kilojoules per 1 mole, because this is 1 mole. So all you really have to really be careful about is that there's a little C, there's your substance in question, and because this is per mole, just make sure that this is 1 mole. No big deal, right? If I give you something like this, all this means is if I give you this, you're going to be able to tell me what the heck is going on. You're going to be able to tell me it's a complete combustion reaction. You're going to tell me that we're talking about methanol, and that the delta H is negative 725.9 per mole of one of these. Okay, no big deal. So method number 2, enthalpy changes. So this is simply just an enthalpy change of reaction. So there's few different steps involved in this. Step number 1, you write out a balanced equation. Find the number of moles of required substance from the balanced equation, the coefficients of and we look at that, we find the number by looking at the coefficients, and we use the formula. Your delta H of the reaction is equal to the number of moles at time, and then your delta H. Okay, another thing too, kiddos, is this. In this particular case, if you have 2 moles of a substance, you just have to take your delta H and multiply it by 2, or depending on what your coefficient is, but I'll explain that. Then report the enthalpy change for the reaction by writing it next to the balanced equation using the appropriate signs. Okay, so now that's the key. In this case here, we're not using that symbol thingy. We're actually writing a balanced equation, and then we're writing down the enthalpy change next to it. So let's look at some examples. So write an enthalpy change beside the chemical equation. And this is what it's going to look like, kiddos. So the enthalpy change is not a molar value. Notice that it's not kilojoules per mole. Okay, it's not. So it's kilojoules. So we're looking at it as it's balanced already. So let me just repeat. The enthalpy change is not a molar value, so it does not require the M subscript and is not in kilojoules per mole. Here's another example. Compare the two. When 2 moles of sulfur dioxide are burned, twice as much heat energy is released as when 1 mole of sulfur dioxide is burned. Okay, so let's take a look here. Notice we have sulfur dioxide, and if if making sulfur trioxide, and it is equating to the delta H of combustion, negative 98.9 kilojoules. Okay, so when we're looking at this case here, because there's 2 moles of it, okay, we actually have to take this number and multiply it by 2 to get negative 197.8 kilojoules, because it's dealing with 2 moles compared to 1 mole. But all you're really doing is you're balancing your equation, and then you are writing your delta H next to it and keeping in mind the appropriate sign. So here's an example taken out of your textbook. Sulfur dioxide and oxygen react to form sulfur trioxide. So that's what we're going to use as a balanced equation. We're going to build our balanced equation based on the information given from your info box or from your information. Like, you get questions like this all the time. The standard molar enthalpy of combustion of sulfur dioxide in this reaction is negative 98.9 kilojoules for every 1 mole, okay? What is the enthalpy change for this particular reaction? So that's what we're looking for. So first step we're going to do is you're going to balance your equation. You're going to write out your balanced equation. When balanced, you get a coefficient of 2 for the sulfur dioxide and a coefficient of 2 for the sulfur trioxide. And it's just like that, so because it has to be balanced. Then we're going to obtain the chemical amount of sulfur dioxide from its coefficient in the balanced equation. So basically we have in this balanced equation of the sulfur dioxide, there's 2 moles here. So we have 2 moles, and we are going to multiply it by the negative 98.9 kilojoules, and that was a given value in your question. Per mole, the moles cancel out, kiddos, and you get negative 197.8 kilojoules. Okay, and again, to repeat, the negative 98.9 kilojoules per mole is for 1 mole of SO2. We need to find 2 moles of the substance. Once we go for 2 moles, the moles go away. So this is the amount for this particular balanced equation. So to make it perfect, we report as follows: 2 SO2 gas plus 1 O2 oxygen gas yields 2 moles of sulfur trioxide, and we have to just make sure that we have the appropriate delta H. Okay? So no big deal, not a big deal. So another example, wild natural gas wells are sometimes lit on fire to eliminate the very toxic hydrogen sulfide gas. The standard molar enthalpy, remember molar enthalpy is per mole, of combustion of hydrogen sulfide is negative 518.0 kilojoules per mole. Express this value as a standard enthalpy change for the following reaction equation. Notice there's 2 moles. Okay, once it's balanced. So what we have to do is we have to keep that in mind when we find the delta H of this combustion reaction. And all you're really doing is just multiplying it by 2. That's it. Because there's 2 moles, I have to multiply that negative 518.0 times 2, right? So this looks more like this. 2 moles of the substance, negative 5, oops, apologies, it's kind of ugly. Negative 518.0 kilojoules. Oh my goodness. I have issues today. That's okay. Kilojoules per mole. Moles cancel out, kiddos, and you get that. And that's all you have to do. Write out your balanced equation and your delta H. All right. Method 3. Oh, this is so easy. Can I just tell you how easy it is? It's so not a big deal. Method 3, energy terms in balanced equations. For endothermic reactions, the energy, the delta H, is actually found in the reactants. Okay, so we have reactants, and then we have our delta H here, and then we have our products. And just once you see the delta H in the reactants portion, you know that it is an endothermic reaction. For an exothermic reaction, the energy is listed along with the products. So reactants, blah, blah, plus blah, blah, yields products, and then you have your energy here in the product section for every single exothermic reaction. Okay, example. Ethane is cracked into ethene in a world scale in world scale quantities in Alberta. Communicate the enthalpy of reaction as a term in the equation representing the cracking reaction. So let's take a look at this delta H. Oh, okay, it's positive. What does that mean? If the delta H is positive, are we dealing with an exothermic or an endothermic reaction? So a positive delta H means that a negative Q, which means that it's endothermic. So if it's endothermic, it's going to go in the reactant portion, and that's all you're doing. It's just, it becomes part of your reactants. So you have reactant plus reactant, which is your energy, and then you have your products. Because it's in the reactants before the arrow, we know that this is an endothermic reaction. See, not even hard. It's not even hard. Okay, so method 4 is my most favorite method. It's my most favorite method because I just love drawing these potential energy diagrams. I don't know why, I just love it. So during a chemical reaction, we have changes in chemical potential energies. Remember, potential energy is opposite of kinetic energy. Kinetic energy is the surroundings, and your potential energy is talking about the system. This means that bonds are breaking and reforming, which of course results in changes in potential energies. We can represent these changes using a potential energy diagram. So these potential energy diagrams are muy importante, and you are going to see them for always now in this unit, and they're so much fun. Some things to remember: if the reaction is endothermic, right, in nature we draw a step up. So let's think about that. So if I were to show a change, if this is like we're looking at Q and we're looking at temperature, temperature goes up. If the temperature goes up, right, if your Q is up, if your Q is positive, your delta H is negative, and that's why it's a step down, okay, because this is your system, and this is data for your surroundings. Okay, kiddos? So if the reaction is exothermic in nature, then we draw a step down diagram. So which means that the temperature is going down. Temperature is going down, that's your Q. Your delta H is opposite, it's going up. That's your delta H. All right, so let's take a look at what that looks like. So here we go, an endothermic reaction. Note that the direction of an arrow is going down. The system is releasing energy, so the temperature goes up. This step down, kiddos, is your potential energy diagram, and it's showing that the temperature is going up. Here's your chemical system. In this case here, energy is taken out into the system, right? The system's temperature goes up. And for your delta H, it's showing a step down. So during an exothermic reaction, the enthalpy of the system decreases, heat flows out of the system and into the surroundings, and we observe a temperature increase. In an endothermic reaction, we note that the direction of the arrow is going up. The system is absorbing energy from the system is absorbing energy from the surroundings. The temperature of the surroundings goes down, right? So this is your kinetic energy. Your potential energy is going up because it's opposite of Q. So in this case here, the energy is leaving the surroundings into the system. So the system is receiving energy from the surroundings, and we have a step up. So during an endothermic reaction, the enthalpy of the system increases, heat flows into the system from the surroundings, and we observe a temperature decrease. So here's some examples. Communicate the following enthalpies of reaction as chemical potential energy diagrams. The burning of magnesium to produce a very bright emergency flare. So if it's a negative delta H, is that endo or exo? Is it a step up or a step down? Also, when you're drawing your potential energy diagrams, please include the reactants and the products. So take a minute, draw it out, and we'll give you the answer. So if you can pause right now, that'd be cool. And this is what you should have got. You have your reactants, your products, and you have a step down. For a combustion of magnesium, that's your title. You have your EP, potential energy in kilojoules, and we just write reaction coordinate on the bottom. Okay, the decomposition of water by electrical energy from a solar cell. We have our delta H of decomposition, or our molar enthalpy of decomposition, to be positive 285.8 kilojoules. So this value is positive. What does that mean in terms of potential energy? And remember, this value is given for 1 mole of water. So very important, when you're writing a balanced equation, make sure it's for 1 mole of water. If it's not for 1 mole of water, you got to change that delta H. So there's the answer. I should have asked you to pause, but you know, you're going to do it anyways. I'm pretty confident. And that's what you should get, kiddos. You have your reactants, you have your products, you have a step up. All right, so this is very important. It's very important that you put in your in the vault, that means in your brain, you have to memorize what is happening with photosynthesis and cellular respiration. Photosynthesis is endothermic, cellular respiration is exothermic. So I'm going to allow you to pause because I want you to express the standard enthalpy changes for cellular respiration and for photosynthesis by using the 4 different methods of communication. 1 mole of glucose is consumed during cellular respiration to release 2,802.5 kilojoules of energy. And we also know that glucose is produced during photosynthesis. So go ahead and show practice with the 4 methods, the process of photosynthesis, and then the 4 methods using the process of cellular respiration. And then pause and then check out the answers. So the solution for cellular respiration using the 4 methods. Take your time to go through them all. Make sure that if you don't understand something, you fix it in terms of looking at the key in your work. And if there's still some questions, please contact me. And here is the solution for photosynthesis. All right, kiddos? And all we have to do is summarize 4 ways of communicating energy changes. You have molar enthalpy, enthalpy change, right? Molar enthalpy, enthalpy change, the term in a balanced equation, and by using chemical potential energies. So that just gives you an example of 4 different ways that we communicate energy change. If you're bored and you got nothing else to do, you can do some reading and some questions. Other than that, there are questions included in your note package along with keys in my Google Classroom. All right, kiddos, that is it. That is all. Have an awesome day.